A pozzolan is a siliceous or siliceous and aluminous material which, in itself, possesses little or no cementitious value but which will, in finely divided form and in the presence of water, react chemically with calcium hydroxide at ordinary temperature to form compounds possessing cementitious properties. The broad definition of a pozzolan imparts no bearing on the origin of the material, only on its capability of reacting with calcium hydroxide and water. A quantification of this capability is comprised in the term pozzolanic activity. Pozzolana are naturally occurring pozzolans of volcanic origin. History. Mixtures of calcined lime and finely ground reactive silicate materials were pioneered and developed as inorganic binders in the antique world. Architectural remains of the Minoan civilization on Crete have shown evidence of the combined use of slaked lime and additions of finely ground potsherds for waterproof renderings in baths, cisterns and aqueducts. Evidence of the deliberate use of volcanic materials such as volcanic ashes or tuffs by the ancient Greeks dates back to at least 500 to 400 BC, as uncovered at the ancient city of Kamiros, Rhodes. In subsequent centuries the practice spread to the mainland and was eventually adopted and further developed by the Romans. The Romans used volcanic pumices and tuffs found in neighboring territories, the most famous ones found in Pozole, hence the name Pozzolan, and in Senai. Preference was given to natural pozzolan sources such as German truss, but crushed ceramic waste was frequently used when natural deposits were not locally available. The exceptional lifetime and preservation conditions of some of the most famous Roman buildings such as the Pantheon or the Pont du Gard constructed using pozzolan lime mortars and concrete testified to both the excellent workmanship reached by Roman engineers and to the durable properties of the utilized binders. Much of the practical skills and knowledge regarding the use of pozzolans was lost at the decline of the Roman Empire. The rediscovery of Roman architectural practices as described by Vitruvius and De Architectura, also led to the reintroduction of lime pozzolan binders. Particularly the strength, durability and hydraulic capability of hardening underwater made them popular construction materials during the 16th to 18th century. The invention of other hydraulic lime cements and eventually Portland cement in the 18th and 19th century resulted in a gradual decline of the use of pozzolan lime binders, which developed strength less rapidly. Over the course of the 20th century the use of pozzolans as additions to Portland cement concrete mixtures has become common practice. Combinations of economical and technical aspects and, increasingly, environmental concerns have made so-called blended cements, that is cements that contain considerable amounts of supplementary cementitious materials, the most widely produced and used cement type by the beginning of the 21st century. Pozzolanic materials. The general definition of a pozzolan embraces a large number of materials which vary widely in terms of origin, composition and properties. Both natural and artificial materials show pozzolanic activity and are used as supplementary cementitious materials. Artificial pozzolans can be produced deliberately, for instance by thermal activation of kaolin clays to obtain metakaolin, or can be obtained as waste or byproducts from high-temperature process such as fly ashes from coal-fired electricity production. The most commonly used pozzolans today are industrial byproducts such as fly ash, silica fume from silicon smelting, highly reactive metakaolin, and burned organic matter residues rich in silica such as rice husk ash. Their use has been firmly established and regulated in many countries. However, the supply of high-quality pozzolanic byproducts is limited and many local sources are already fully exploited. Alternatives to the established pozzolanic byproducts are to be found on the one hand in an expansion of the range of industrial byproducts or societal waste considered and on the other hand in an increased usage of naturally occurring pozzolans. Natural pozzolanas are abundant in certain locations and are extensively used as an addition to Portland cement in countries such as Italy, Germany, Greece and China. Volcanic ashes and pumices largely composed of volcanic glass are commonly used, as are deposits in which the volcanic glass has been altered to zeolites by interaction with alkaline waters. Deposits of sedimentary origin are less common. Diatomaceous earths, formed by the accumulation of siliceous diatom microskeletons, are a prominent source material here. Use. The benefits of Pozzolan use in cement and concrete are threefold. First is the economic gain obtained by replacing a substantial part of the Portland cement by cheaper, pollution-free, natural pozzolans or industrial byproducts. Second is the lowering of the blended cement environmental cost associated with the greenhouse gases emitted during Portland cement production. A third advantage is the increased durability of the end product. Additionally, the increased blending of pozzolans with Portland cement is of limited interference in the conventional production process and offers the opportunity to create value by converting large amounts of industrial and societal waste into durable construction materials. Current practice may permit up to a 40% reduction of Portland cement used in the concrete mix when replaced with a carefully designed combination of pozzolanic materials. Pozzolans can be used to control setting, increase durability, reduce cost and reduce pollution without significantly reducing the final compressive strength or other performance characteristics. The properties of hardened blended cements are strongly related to the development of the binder microstructure, that is, to the distribution, type, shape and dimensions of both reaction products and pores. The beneficial effects of Pozzolan addition in terms of higher compressive strength performance and greater durability are mostly attributed to the pozzolanic reaction in which calcium hydroxide is consumed to produce additional CSH and CAH reaction products. These pozzolanic reaction products fill in pores and result in a refining of the pore size distribution or pore structure. This results in a lowered permeability of the binder. The contribution of the pozzolanic reaction to cement strength is usually developed at later curing stages, depending on the pozzolanic activity. In the large majority of blended cements, initial lower strengths can be observed compared to the parent Portland cement. However, especially in the case of pozzolans finer than the Portland cement, the decrease in early strength is usually less than what can be expected based on the dilution factor. This can be explained by the filler effect, in which small SCM grains fill in the space between the cement particles, resulting in a much denser binder. The acceleration of the Portland cement hydration reactions can also partially accommodate the loss of early strength. The increased chemical resistance to the ingress and harmful action of aggressive solutions constitutes one of the main advantages of Pozzolan blended cements. The improved durability of the Pozzolan blended binders enables to lengthen the service life of structures and reduces the costly and inconvenient need to replace damaged constructions. One of the principal reasons for increased durability is the lowered calcium hydroxide content available to take part in deleterious expansive reactions induced by, for example, sulfate attack. Furthermore, the reduced binder permeability slows down the ingress of harmful ions such as chlorine or carbonate. The pozzolanic reaction can also reduce the risk of expansive alkali-silica reactions between the cement and aggregates by changing the binder pore solution. Lowering the solution alkalinity and increasing alumina concentration strongly decreases or inhibits the dissolution of the aggregate aluminosilicates. See also, alkali aggregate reaction, calcium silicate hydrate, energetically modified cement, cement chemist notation. References: Meta, P.K. Natural Pozzolans, Supplementary Cementing Materials in Concrete. Carmit Special Publication 86, €1.33. Snellings, R. Mertens G. Elson J. Supplementary Cementitious Materials. Reviews in Mineralogy and Geochemistry 74, 211 €278 doi, 10.2138/RMG. 2012.74.6. Spence, R.J.S. Cook, D.J. Building Materials in Developing Countries. Wiley & Sons, London. Adorn, M.G. Concrete Progress from the Antiquity to the Third Millennium. London, Telford. Schneider, M. Roma M., Student M. Bolio C. Sustainable Cement Production, Present and Future. Cement and Concrete Research 41, 642 €650 doi, 10.1016/J. Semkenas. 2011.03.019. Capex, T. Scrivener K. Alkali fixation of CSH in blended cement pastes and its relation to alkali-silica reaction. Cement and Concrete Research 42, 1049 Euro 1054. doi, 10.1016/J Semkenas. 2012.03.010. Cook D.J. Natural Pozzolanas. In, Swamiya N., Editors Cement Replacement Materials, Surrey University Press, pages 200. McCann A.M. The Roman Port of Koza, Scientific American, Ancient Cities, pages 92 Euro 99, by Anna Marguerite McCann. Covers, Hydraulic Concrete, of Pozzolana Mortar, and the Five Piers, of the Koza Harbour, the Lighthouse on Pier 5, diagrams, and photographs. Height of Port City, 100 BC.